So in this video, we're going to show an application of Rolle's theorem to a higher degree polynomial. In this case, it'll be a 6th degree polynomial. And because this homework is about Rolle's theorem, it's always going to be the expectation that you explain why Rolle's theorem can be used. In other words, you need to show that the 3 criteria that guarantee Rolle's theorem can be met are met by the function that you're working with in order to receive credit. So it says, let f of x equal x to the 6th minus x to the 4th. Find all values of c in the open interval from -1/2 to 1/2 such that the derivative at c is equal to 0. So first we want to show that Rolle's theorem guarantees. We want to show that there's a guarantee that there's an input value c on the open interval that such that the derivative at c is going to be equal to 0. So we're going to use Rolle's theorem to guarantee that such a value exists. Once we guarantee it exists, then we will find it. So to indicate that we've met criteria 1, what we want to notice is that this is just a 6th degree polynomial. All polynomials, regardless of their degree, have domain -infinity to infinity. So I can say, because f of x is a polynomial, it has domain. So I'm showing criteria 1 is met. It has domain -infinity to infinity. So it will clearly be continuous. Nothing bad is going to happen. Continuous over the closed interval. We need to explain that it's going to be continuous over a closed interval. So it's going to be continuous over the closed interval from -1/2 to 1/2. So we want to show there's a value of c on the open interval, but first we need to explain why we understand that it will be continuous over the corresponding closed interval. To show that the second criteria has been met, we need to claim something about differentiability, but f of x is a polynomial. So we want to note that all polynomials are differentiable over their domain. In other words, all polynomials can be differentiated on the interval from -infinity to infinity. Nothing's going to matter. We're only going to apply 2 rules, the constant multiple rule to take derivatives and the power rule to take derivatives, and that's all we need. And we aren't going to get anything that's undefined or have a division by 0 or have to take the square root of a negative. Nothing bad happens with polynomials. So clearly, because f of x is a polynomial, clearly f of x, our function, is differentiable over the given open interval. So we meet criteria 2. Criteria 3, we need to show that f of -1/2 equals f of 1/2. But here what we want to recognize is f of x is an even function, right? So from pre-calculus, if we plug in the opposite of x into a function, so plug in the opposite of x into a function, and we wind up, hey, this is the 6th power, it's going to kill the negative. This is the 4th power, it's going to kill that negative. And we wind up getting the same thing that we would have gotten just by plugging x into the function. So in other words, when f of the opposite of x equals f of x, we have an even function. So I can recognize that this is an even function by looking at the degree of the individual terms. They're even terms in a polynomial. This is an even function. So here I can say I can notice from pre-calculus, without having to do any work, I can notice I have an even function. Note that f of x is an even function. This is from pre-calculus, and this is why we discuss these ideas in pre-calculus, so we could use them, is an even function. F of negative 1/2 equals f of 1/2. I don't need to plug the numbers into the function to figure that out. But when I plug in 1/2 or negative 1/2, the negative is going to just be killed by the 6th and the 4th powers. So I'm just going to get the same output. I want to recognize it. So all three criteria are met. I know that there is an input value c on the interval from negative 1/2 to 1/2 at which the derivative is equal to 0. Now my job is to find that value of c. So I'm going to take my function. I'm going to take the derivative of my function. I'm going to set my derivative equal to 0. I want to look at my function and recognize that it can be factored. I can pull out a 2x cubed term. And if I do that, I'll be left with the 3x squared minus 2. And now the zero product property says that either 2x cubed is equal to 0 or 3x squared minus 2 is equal to 0. Here, I'll get that x is equal to 0. And from here, I'm going to get that x squared is equal to, add 2 to both sides and divide by 3. Take the square root of both sides, so I'm going to get plus or minus the square root of 2/3. And so clearly 0 is in this interval. What I need to figure out is plus or minus the square root of 2/3 in the interval from negative 1/2 to 1/2. So what I want to notice is that 2/3 is greater than 1/4, right? Smaller numerator, bigger denominator. This number is smaller in size than this. I'd rather have 2/3 of a pi than 1/4 of a pi. So now take the square root of both sides. This is going to simplify to 1/2 is less than the square root of 2/3, and this tells me that negative 1/2 is going to be less than negative square root of 2/3. Sorry, get this all backwards. This tells me that negative square root of 2/3 is going to be less than negative 1/2. When we negate things, we flip them over the 0. So 0 lies in between negative 1/2 and 1/2. But because the square root of 2/3 is bigger than the square root of 1/4, which is 1/2, we're going to get that plus or minus the square root of 2/3 falls outside of this interval. So Rolle's theorem guaranteed there was a number in this interval for which the derivative was equal to 0. Here we get the derivative as 0 at 3 different input values, but only one of them meets the criteria. So 0 is an element of the interval from negative 1/2 to 1/2 is the value that we're after in this case. And notice that you could change the interval so that all three of these were included. So for example, if I had asked instead find all values of c on the interval, let's say I'd asked to find all values of c on the open interval from negative 4 to 4 instead. Well, negative 4 is down here and 4 is up here, so then all three values minus the square root of 2/3 plus the square root of 2/3 and 0 all would have fallen in this interval, and I would have had more than one value of c for which the derivative was equal to 0 inside the interval of interest. The argument I would have made would have run basically the same. I just would have been changing the negative 1/2 and the 1/2 to negative 4 and 4. So again, Rolle's theorem, if the three criteria are met, Rolle's theorem just guarantees there's a number in that interval for which the derivative is going to equal to 0. It doesn't tell you any information about how many numbers in that interval will have a derivative, will generate a derivative of 0. It could be 1. Rolle's theorem guarantees 1. It could be more than 1. Depending on the interval you're working with, you could get values like we did in this case that fall outside of that interval, so you need to check for that.